Hello, you're watching Unit 3, Lesson 2, Vectors in 2 Dimensions. Today we're going to be talking about adding vectors in 2 dimensions and then finding a resultant. So the first thing I want to start off with is just this word resultant. Resultant. All this really is your sum of vectors. So let's take a step back from vectors. Let's just say we're adding normal numbers. So if we have, let's say, 5 plus 3 plus let's just say -2, right? If we took the sum of this, we would get, well, we have 8 here, minus 2, we get a positive 6, right? In the same way, well, this part right here that we added, that's our sum. Right, when we have adding with vectors, instead of getting the sum, we get the resultant. So if we're adding the same one, we have a vector that's 5 units long, a vector that's 3 units long, and a vector that's -2. Right. So if we were to add these in the correct way, which is the tip to tail method, right, we take this one and we're going to move it to the tail of that one, and then we're going to take this one, I'm going to move it to tail this one, and it's not going to go like that, right? We don't just stack them in front of each other, but it's going to go so that the head of the second arrow meets the tail of the third arrow, right? And approximately this is supposed to be about 2 units long, so we're going to put it right there. Now we see that this vector ends right here on this line, and it started right here. That was our starting point. So if we were to draw a line, not a line best fit, draw a vector from our start point to our end point, that would get us a vector that goes all the way like this. And this vector, if we count the units, is 1, 2, 3, 4, 5, 6 units long. So this is 6. We would give it a unit, maybe boxes. But then this also has a direction. We would say to the right. We could also say that if right was our positive direction, we could also just say a positive 6 boxes. So this should be something you're a little bit used to already. We may have not used the word resultant too often, but all you really need to know is the resultant is the sum of your vectors. And so far we've only done vectors in 1 dimension, right? So next word we want to talk about is a dimension. So dimension is just a direction that you can go into. In our life, right, we can go up and down. So that was a really badly drawn arrow. We can go up and down. We can go left and right. But then we can also go in and out. Right? So if you can imagine, this would be like into the screen or out of the screen. So we live in a 3-dimensional world. So far we've only ever been doing, though, just 1 dimension. Just forward or backwards, or only up and down, or only in and out. Right? We rarely go in and out because that's just kind of more confusing. It's difficult to draw. So what happens though when we, instead of going in 1 dimension, we go in 2 dimensions? Well, we can get vectors that kind of rotate. So let's see what happens. Let's see what happens if we have, for example, what if we have a vector that goes like this, and then a vector that goes like this, right? We're going to add them the exact same way, but right, we're not going to get just a line. We can't just add them the normal way that we're used to adding them. So first, I want to talk about the method that we use. I mentioned it a little bit earlier, but it's called the tip to tail method. So tip to tail method, or it's also known as like the head to tail method. And all this really states is that when you're adding vectors, you don't want to add them so that 2 arrowheads are touching or 2 tails of the arrows are touching. So for example, if we go back to this one, this example right here, we had a 5 box long arrow, we had a 3 box long arrow, and then we had a 2 going in the negative direction. Well, we could have connected these lines in many different ways. We could have taken this one, for example. Let's try that again. We could have moved it, I don't know, like right here. Right? But that doesn't really help us. We're not really adding it. If this was, for example, someone maybe moving, right? If they moved 5 miles right, or maybe east, and then they moved 3 miles east, they'd then be 8 miles away from their starting point, right? So our starting point being right here in this spot, and our ending point being right here, right? Our resultant would then be from our starting point to our ending point, which is just a line that is that long. Well, we also had this other one going backwards the way that we came. So this person didn't only go 8 miles east, they also went 2 miles west. And so we would go back this way, and we get back to our resultant that we had originally over here in the red. Something else to notice is that the order in which you add vectors doesn't matter. So if we were to move these vectors back to where they started, let's say instead of starting with that 3 vector, let's start with the 2 vector, right? We could take this one first, and we'll move it right on top here, and then we'll take this one, and we're gonna wanna start at the head of that second arrow, which starts right here. Well, now if we measure this, we have 1, 2, 3, 4, 5, 6. We still get 6, our resultant's still there. Even so, we can add it in a different combination. We can start with the 2 vector pointing that way, and we can take the 5 and the 3. So let's take the 3 first, right? Start here, we go this way, and then we take this other one right here, and we go this way. And you might be thinking here, this one looks a little bit confusing. It almost looks like it is 1, 2, 3, 4, 5, 6, 7, 8 units long, but that's not true, because our starting point was actually right here, and our ending point was right here. If we measure this, 1, 2, 3, 4, 5, 6, it's still 6 units long. So order does not matter. So when we're adding vectors, order in which you add it, order of adding vectors does not matter. So keep that in mind. However, if you put and move vectors and connect them in the wrong way, not using the head to tail method, then you're just gonna get the wrong answer. So the order should never matter, but sometimes there are orders that just look nicer. So then going back to this problem over here, let's do the tip to tail method. There's 2 ways we can do this. We can take, we'll call this one vector A, we'll call this one vector B. We can take vector A and move the tail of vector A to the head of vector B, or take the tail of vector B and move it to the head of vector A. Just to conserve space, I'm gonna take vector A and move it to vector B, because again, order does not matter. So I'll take this, I'll move it, and we'll put them right there, right? And so our starting point then is right here. So let's zoom in on this guy right here. And our ending point is right here. And this is supposed to be a perfectly box length. So sorry that I'm a little bit off, but it should be about right there. So we have these 2. And again, results in some of the vectors. It's just the vector length from your starting point to your ending point. And so for our case, we would have a vector that is about that long. And the question with this might be like, how the heck do we figure out how much that vector is? I'm going to redraw this because I didn't perfectly line it up. Right? Well, you might notice that this is actually a right triangle. So if we knew the amount of B and we knew the amount of A, we can just use the Pythagorean theorem. And so just really quickly to review, the Pythagorean states that if you know 2 sides of a right triangle, you can know the 3rd side. And it's by this simple formula. So we have A squared plus B squared equals C squared, where A and B are the non-hypotenuse sides of your triangle, and where C is your hypotenuse. Right, so let's pretend, for example, in our problem, we'll make it easy. We'll say that B is 3 and A is 4, and that's approximately true. I'm a little bit off kind of right here, but don't worry about it. So essentially we have a 3, 4, 5 triangle, but we can still write this out. If we plug in A and B for our vectors, we have 3 squared plus 4 squared equals C squared. Well, we want to get C by itself, so we're actually just going to square root both sides. So then we actually end up getting the square root of 9 plus 16, and that equals the square root of 25. In physics, we don't have radicals, so we're just going to take the square root of 25 and we get 5. In our case, we're measuring boxes, so we have 5 boxes. Not only that, but if this is a vector, right, we need to find an angle. And we're not going to spend too much time on that. I might show you a little bit later, maybe in this lesson or the next, but the answer that we get here then is the magnitude of our resultant. So this is just the magnitude of the resultant. For this to be a true resultant, we're also going to need an angle. We also need that angle. So what we've done here is we've gotten 2 vectors that were luckily at right angles, and we were able to figure out what the resultant was. But then the question becomes, what happens if we essentially get 2 vectors that are not at right angles? So let's do a new problem. So let's say we have vector A. Vector A goes maybe something like this, right? And that's supposed to end right at that mark. This is vector A. And maybe vector B is, let's say, just like that. This is vector B. So first, you can kind of tell here, it's not going to be a right triangle. We're not going to get that right triangle. So it's going to be difficult to find. We can't use Pythagorean theorem. Keep in mind, Pythagorean theorem only works for right triangles. But something really nice that we can do is if we have graphing paper, we can actually break these vectors down into their components. So into their components. So what a component is the horizontal, or we should say the parts that make up a vector. So the parts, in our case, they're going to be horizontal and vertical parts that make up a vector. So what we can do for this one is break these down. So first, let's just draw these out. So we know that A, if we take A and add it to B, we're going to get something that looks like this. Oops. Right, and if we were to draw the resultant of that, we go from our start point to our end point, we get something that looks a little bit like that. And that's, well, how are we going to figure that out? If you know law of sines or law of cosines, you could figure that out. But off the top of my head, I don't know those. What we can do, though, is let's just move this R, this resultant, somewhere else. So let's just see, it goes up 5. I think 1, 2, 3, 4, 5, and it goes over 3. So let's just draw that again. 1, 2, 3, 4, 5, over 3, 1, 2, 3. Right, and now what we can do is we can actually just break it into its components. So this red vector, our resultant, is actually made up of 2 vectors, a horizontal and a vertical one. So using purple, I'll draw our vertical one. And then using blue, I will draw our horizontal one. Right, so this has a value of 3 boxes. And our purple one has a value of 4 boxes, or I think 5 actually, 5 boxes. Well, if we look at this, this actually is a right triangle. So something that you will find out is that any vector that is not either north, perfectly south, east, or west can be broken up, say if we have something like this, into a vertical and a horizontal component. So we have these 2, and now we actually can find our resultant. It's actually not too hard. We do 5 squared plus 3 squared, take the square root of that. We're going to get 25 plus 9. And that gets us about, let's see here, 34, square root of 34. And if we use some math, the square root of 34 equals, we get about 5.8 boxes. If we look at this, it kind of does look about 5.8 boxes. So that's really easy. That makes things a lot nicer for us. So what we do is we can still draw our resultants, but then we just take away those A and B vectors, right? This might look a little confusing because when we have this one right here, right? This A and this A and this B are different from these components. But let's also keep in mind that going back to just our normal sums, there are many ways that we can get 6. We can have 3 plus 3 plus 0. We can have 1 plus 1 plus 4. We can have 3 plus 2 plus 1. There's so many different combinations that you can use to make the number 6. And in the same way, there are different combinations that we can make our resultants. And the best and easiest ones that we can do are ones that give us right triangles, because that way we can use Pythagorean theorem. Yet there's also one more way that we can figure out the resultants of the magnitude of a resultant. Technically speaking, we still have not figured out this angle, and so we can only figure out a magnitude. So again, this is a magnitude, and that just means an amount. It does not have any direction. So let's just take A and B again. So B, if I recall, goes up like that. A goes up something like that. So what we can do with these is we can actually break these down. This is B, this is our A. So if I broke these down, well, B is made up of a vector that is 2 boxes that way. So I'm just gonna use 2B, and then we have 2 boxes that way. Vector A is made up of 1 box this way. Sorry, let me draw my arrows. And 3 boxes this way. Well, what we can do is we can take our vertical ones and we can add them together. So we have 2 plus 3. That gives us 5. So we'll draw a 5 box long arrow. And then we can take our horizontal ones. So that's 2 and 1, and draw a 3. Horizontally 3. Okay, so this is 3, this was 5. And if we look back to our old one, right, that's the exact same thing that we just made. So our resultant, again, I'm just using random colors at this point just so I can differentiate. Right here, here's our resultant. This resultant is the exact same as the one that we had right here. So what we can do is we can break down each of these components into, each of these vectors into their components and add the ones together that are going in the same direction. We can't add, if we add this 2b to this 2b, that gets you 4b. That doesn't actually tell you how long this b is. Because if we look right here, this b is definitely not 4 boxes long. 4 boxes long would be maybe something over here. But if we take things that are in the same direction and add them together, we can make the components of our resultant and then eventually just figure out our resultant. So I think that's all that I want to go over for now. If you have any questions, again, please ask me so that I can help you out. Technically speaking, right, you could have more than 2 vectors. You can have like 9 if you wanted to. And if you just broke them all down, added all the vertical ones together and added all the horizontal ones together, you get the same resultant. One quick thing to mention is what happened if B was instead in this direction, right? Well, this one, rather than being to the right 2 boxes and down and up 2 boxes, is actually down 2 boxes. So this is actually a -2 box. Go across, this is -2 boxes. So if we were to add this to vector A, we're actually going to get something a little bit different. We're actually going to have a vector that is up 3 and across only 1. We'll talk about this more in the next video. So just keep that in mind. If you're not understanding that part yet, don't worry about it. We're just talking about directions too, as well as we add while we add vectors. So yeah, that's all I have for you guys today. Have a good rest of your day.